Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional unceded lands of the Lekwungen peoples.
Good morning and welcome back to Stories from Space. I'm your host, Matt Williams.
Today, my guest is none other than Dr. Stephen Vance, a NASA scientist with NASA's Jet Propulsion Laboratory, the former supervisor of the Planetary Interiors and Geophysics Group, and the current deputy manager of the Planetary Science Section at JPL. Dr. Vance, welcome aboard.
It's great to be here. Thanks for having me.
Well, thank you for coming on. So, as my listeners may recall, in a previous episode, we discussed ocean worlds, referring to icy moons in the outer solar system that have interior oceans and could possibly harbor life. And Dr. Vance, this is your specialty, isn't it?
That's right. That's what I do. I study the interiors of ocean worlds. I started my career thinking about Europa. I've since extended my interests to Jupiter's moon Ganymede and Enceladus, and basically anywhere there's liquid water under ice in the solar system.
Now, looking at your JPL page, it is really quite impressive here. You've worked on a number of missions, including the Cassini-Huygens orbiter and lander, the Mars Insight lander, and the Mars Exploration rovers, and that would include NASA's Spirit and Opportunity rovers.
So yeah, I've had some tangential involvement in some stuff there, and an interest generally in what InSight did. But my main role is on Europa Clipper, and I make use of Cassini-Huygens data to think about what the interiors of Titan and Enceladus in particular might be like. But yeah, my main mission involvement is with Europa Clipper.
And that certainly came up in our previous episode. Now, before we get into all that, though, I'd like to have you tell us a little bit about yourself. What was the road that brought you to NASA JPL and to the position of Deputy Manager of the Planetary Science Section?
Sure. Yeah, it's a common trope in planetary science. A lot of my colleagues were influenced by Carl Sagan, and I am also part of that trope. So I work with people who, worked with him or just simply were inspired by him. And so I felt like I was in good company stepping into an interest in planetary science, being someone who was really excited about the Contact movie and book in the 90s. Contact being a fictional work in which Sagan and co-authors imagined receiving a coded message in radio from an exoplanet, or at least from beyond our solar system. Yeah, so that kind of interest in eventually contacting intelligent life really fed into my already growing interest in the nature of the universe and how the planets work. It just happened that when I was completing my undergraduate degree in physics at UC Santa Cruz, NASA inaugurated the field of astrobiology after the discovery of possible life in the ALH 84001 meteorite, that is the Allen Hills meteorite discovered in Antarctica. So there was a lot of fertile ground for me to develop my interest in planetary science and the search for life in the universe. And it also just happened that Galileo, the NASA spacecraft, was exploring the Jupiter system around that time and had just returned really strong evidence for an ocean currently present in Europa. That evidence coming mainly from Europa's magnetic field, which is generated in response to Jupiter's changing magnetic field. So that was the thing that got me into planetary science. And so in my graduate work at the University of Washington, I studied astrobiology, just thinking about the possibility for life elsewhere, how we might imagine life elsewhere might get by based on the extremes of how life works on Earth. So, thinking about life at the bottom of the seafloor on Earth and hydrothermal systems, thinking about life living in ice in Antarctica, that sort of thing. Yeah, so I did a lot of research as an undergraduate, had a lot of fun studying different fields, science related to astrobiology, and long story short, ended up with a postdoc at JPL that turned into a job, and I continued to do things that build on the work that I did as a graduate student. So I'm lucky that I developed that fertile ground on which I started and continue to do work that I'm really excited and passionate about.
Yeah. Well, I'm glad you mentioned Contact by Carl Sagan because, yeah, me too. Seeing that in the 90s was a really major boost to my interest in all things space related. And yes, if anyone has not either read the book or seen the movie, yeah, I'd recommend doing both.
Yeah, and the
And
sci-fi holds up, yeah, even after 20, 30 years.
yeah, so in terms of Europa itself, it was a long road getting to this point, wasn't it? Where we would send a mission out there to explore it directly, rather than an orbiter that was just passing through the system, or one that was like the Galileo probe, studying Jupiter and Juno as well, but making flybys of Europa and gathering new data.
Yeah, it's been a really long road. Starting with the antenna failure on the Galileo spacecraft. Galileo was meant to have a high gain antenna to beam lots and lots of data back to Earth. And if that had opened, I think Galileo would have given us a similar sense of the Jupiter system, the same volume of data, a similar volume of data to what we got from Cassini, which globally mapped Titan at fairly high resolution using its radar, gave us a whole lot of data relevant to Enceladus. By contrast, all of the information for Europa can fit on a CD-ROM, it's less than a gig, less than a gigabyte. So, just during the Galileo days, there were on one hand some exciting, compelling discoveries that we made, and on the other hand, a sense of frustration with what we might have had. And so people were already busy formulating mission ideas as early as 1999. There's the name Europa Clipper, in fact, is on record back in 1999 for studies people were doing of a follow-on mission to the exciting discoveries of an ocean at Europa. So yeah, I got into helping out with that effort when I came to JPL in late 2007. And at that time, I thought we were going to have our flagship mission to go and orbit Europa within a few years. That was kind of the general feeling from the community. But instead, we ended up working on lower cost, more effective mission studies and didn't get going on the main flagship mission until 2015. By then, we had arrived instead of an orbiter at a multiple flyby mission because it turns out because of Europa's radiation environment, you can do a lot more with your available hardware by flying by Europa a bunch of times in an elliptical orbit that keeps you out of that radiation environment and allows you to beam back lots of data to Earth while you're on the long part of your orbit around Jupiter. This is similar to the strategy that Juno employed with its soon to be concluded exploration of Jupiter. And you might have seen the exciting images of Io that were just sent back in December from Juno. So Juno is part of that long road as well. We've learned a whole lot about Jupiter in the meantime. And Juno gave us some updated images of Europa, so kind of a teaser for Europa Clipper.
Oh, yes. Well, and I'm glad you mentioned Io and also the nature of the orbits, how those play a role. Yeah, for those who haven't seen those images, they were just stunning infrared images of the surface of Io and showing just how volcanically active it is. Just looked like a whole bunch of embers in a fire. Oh, it's beautiful. And so Jupiter's radiation environment. In this, in fact, not just its powerful magnetic field, but the magneto tail that the moons pass through, this makes the prospect of humans living there pretty limited, right? Pretty bleak.
Yeah, I wouldn't want to live on Jupiter. Just to elaborate on some of what you were saying. Io spews a bunch of materials into space because it's so volcanically active. Jupiter has an immense magnetic field, the influence of which would appear larger in the sky than the full moon if we could see the magnetic field of Jupiter, despite Jupiter being so far away. So that magnetic field grabs onto solar wind particles, and the field environment ionizes the stuff coming out of Io. And so altogether, you have a really intense radiation environment in the region at the orbital distance from Jupiter that Io and Europa sit at. So yeah, that really intense radiation environment is bad for spacecraft, even worse for people. And so yeah, maybe in the long distant future or in the imagination of a science fiction author, we can easily embed ourselves just a few meters below the ice where we would be protected from that radiation. And then you'd have lots of ice to work with. But the idea of walking on Europa's surface for more than a minute or two, and even then, in a really thick Iron Man suit, is not very appealing. It's a dangerous environment.
And so, yeah, in fact, proposals for settling on any of Jupiter's moons, which was the subject of another previous podcast, settling on the Jovians. In the case of just about everywhere but Callisto, it is strongly recommended that if there's going to be any human settlements, they need to go beneath the ice. And so, in a way, we'd be taking a bit of a page from what we hope is the life that exists there right now.
Yeah, that last point, I'm hopeful there as well. I don't know what we'll find at Europa, but there's an outside chance that there's something there and that we might find some biosignatures, even with Europa Clipper, although I want to emphasize that's not the main goal of Europa Clipper mission. That search for life is deferred to a future mission that has instruments specifically designed for life detection. All
Yeah.
that said, Europa Clipper will bring with it a really, really capable mass spectrometer and a whole lot of imaging instruments that will be able to characterize the chemistry of Europa's surface and the composition of materials that are ejected from Europa's surface, either by impacts, including micrometeorites, dust that's constantly bombarding Europa's surface, or even by plumes if eruptive features exist.
Well, thank you. That's actually my next question, which is what exactly will the Europa Clipper do? And well, you just summarized it there. Basically, it's going to examine the surface, study the chemical composition of the ice sheet, and learn more about the interior ocean, right? And now, if the mission goes well, and the mission does in fact find evidence of potential biosignatures, biomarkers, so what then? Are we talking a Europa lander?
Yeah, Europa Lander is something that's been studied. Actually, that big effort almost led to a flagship mission to follow immediately on Europa Clipper. That did a lot to quantify what it would take to thoroughly search for life. They had an approach that would have had a lot of redundancy in a good way. That is, multiple instruments trying to provide multiple lines of evidence for possible biosignatures. That if you were looking for life on Earth in Antarctic ice, you would have a reasonable chance of finding it by sampling a reasonable chunk of ice and looking for amino acids, looking for cells that had been the remnants of cells that were deposited, and for polysaccharides, the remains of metabolism, I'll say. And so, and you could also look for isotopic signatures in organics embedded in the ice. So those are the sorts of things that the Europa lander was going to do. And that effort also spurred a lot of activity in terms of NASA funded efforts to develop the next generation of mass spectrometers, advanced Raman sensors, things that would give better fidelity in terms of distinguishing different organic molecules, developing really capable cameras that would allow you to do a lot more than current microscopic imagers can do, and packaging them in really small packages that would allow you to get a really capable payload into a really mass constrained setup. So all that being said, while we've had a lot of progress in the field of astrobiology in that sense, just from this vision of landing on Europa, at the same time, there have been efforts toward thinking about drilling through Europa's ice, or the ice of Enceladus, I should say. This is something that Stone Aerospace has proposed doing for quite a long time. But anyone who's tried to drill through Antarctic ice will tell you that those efforts usually take massive equipment, more akin to what you use for oil drilling, with lots of diesel generators and lubricants on your drill bits, things that you wouldn't want if you're looking for life, and things that are prohibitive to a space mission where you have to be as mass efficient as you can, and you wouldn't be able to bring that sort of equipment with you. So there's interest, nevertheless, in how we might autonomously drill through the ice. And I'm excited to see where that goes in the next decade or so, in the time frame that we might consider taking another shot at developing a Europa lander. Maybe we'll be able to get further into the ice with this next effort. Or maybe we'll continue with the previously studied Europa lander. Those are both really great efforts. All of that is to say that there's continued work on this topic.
So Europa Clipper will be launching on October 10th, 2024. That's what this current schedule indicates. And will be arriving around Jupiter in 2030. At which point it's going to commence orbiting Jupiter and making multiple flybys of Europa.
Yeah, that's right. So the launch window for Europa Clipper opens on October 10th. I think we've got about a month if there's any kind of launch problems on the first day or two. I'm really hoping we're going to launch in the first day or two because that's when I'll be there. And then we've got a really long cruise. We'll pass by the Earth, we'll pass by Mars. We'll use those to slingshot ourselves to Jupiter, arriving in Jupiter around 2030, as you say. And then we'll spend about a year getting into position to fly by Europa. As part of that, we'll fly by Callisto and Ganymede as well. So yeah, it's going to be a long journey. On the science team, we're thinking about what we're going to do with our time for the next 6, 7 years or so. I've got a lot of research planned. I think that's okay. The time will go by fast, given that a lot of us have been thinking about this for 20 years or more. But once we get there, the overall goal of Europa Clipper is to both explore Europa and investigate its habitability. That exploration, in part, includes thinking about that future lander that you mentioned, but it also involves looking for what kind of geological activity is happening on the surface, thinking about the timescales over which Europa's surface evolves, and overall thinking about confirming that the ocean exists and trying to figure out its composition. So we have goals to figure out Europa's salinity to within some constraints and to figure out the transport of materials between the ocean and the surface, both materials coming out of the ocean and materials going into the ocean. Since one of the really exciting things about Europa is that the radiation environment generates oxygen at the surface by breaking up water, and that oxygen might be a source for life. So the overturning rate of the ice then becomes a proxy for the delivery rate of oxygen into the ocean. So then you can imagine if we have that constraint on that rate, then we can think about how the ocean might have changed through time. And by measuring the chemistry of the surface and the chemistry of material coming out of the ice, we can put direct constraints on the pH of the ocean, also the salinity of the ocean, and thereby get a sense of the availability of oxygen, the chemistry of the ocean, what kind of metabolisms might take place in the ocean.
And that, in fact, the nature of the icy crust there and the evidence that there is resurfacing, this is part of what led scientists to theorize about the interior ocean in the first place, isn't it?
Yeah, I'd love to step back in history a little farther to the 80s, even the late 70s, when the Voyager spacecraft launched, and there were two of them. It's a different time for NASA. These two very capable spacecraft that had the goal to explore each of the large planets. It happened that at that time, some researchers, Stan Peele and others, who were thinking about tidal interactions, that is, how different bodies orbiting a large planet interact, realized that there might be a lot of tidal energy due to the eccentricity of Jupiter's moons that might lead to volcanism on Io. And then lo and behold, Voyager observed that volcanism. So that to me is one of the favorite story of science, that people were able to use basic physics and some simple observations of a system to make some pretty profound predictions that immediately turned out to be verified. But the Voyager flybys of Jupiter that confirmed the volcanism of Io, they also revealed Europa. They transformed Europa from being a blurry point of light in the sky, as seen through telescopes, to being this really curious looking icy ball crisscrossed with fractures throughout its surface. If your listeners have not seen pictures of Europa, I encourage them to immediately go and search for it online, and they'll see this wonderland of geophysics and geology. One of the remarkable things, though, about that first detailed observation of Europa is that it has strikingly few craters. And you can imagine craters being a convenient marker for how geologically old something is. So crater counting and crater statistics, that is the numerical distribution of crater size, counts of the number of craters of a given size. Those are used with some informed models for how cratering might work through time, basically the statistics of how frequently a given body might be impacted relative to its place in the solar system and its size. That gives you a sense, the number of craters gives you a sense of how old the body is. And so the fact that Europa has only a few large craters has been used to infer that Europa's surface age is probably no greater than 200 million years. So Europa has been basically erasing evidence of past impacts. The ice has been overturning. It's a geologically active place. And so the geological activity was immediately jumped on to infer that there's likely to be, the ice is not that thin, they're not that thick rather, because it's easier to churn about and move the surface if the ice is active, and it's easier for the ice to be active if it's thin. Now there's some nuance there in that the ice can actually be quite a lot thicker if it undergoes solid state convection. But generally you still need heat to cause the ice to be mobile in the first place. And the amount of heat observed at Io can be scaled to Europa based on the tidal parameters, the lower eccentricity of Europa, and you get a pretty high heat flow just from your prediction there. And that heat flow, you can model how thin the ice has to be to get that heat out, and it can't be more than, a few tens of kilometers, even if convection is happening. So again, a thin ice shell suggests that there's an ocean, but the naysayers can still respond and say, well, yes, you need to have had a thin ice shell at some point to get that activity. But what if that activity happened some time ago, and since then the ice is frozen? So all of this is to say that the young surface age itself isn't definitive evidence for an ocean. So it was really critical to have that follow-up with Galileo to observe the changing magnetic field. That was the thing that really gave us a compelling sense that there is an ocean currently at Europa. Nevertheless, as I said, a goal of Europa Clipper is to confirm the presence of an ocean at Europa. And after that confirmation, which I'm pretty confident we'll get, we have a lot that we can do to characterize that ocean and understand its habitability.
Yeah. In fact, that's a fair point. At this juncture, we can't say with absolute certainty, yeah, Europa has an ocean in it. Much like many of the ocean worlds, it's modeling, simulations, and all these hints that point towards the existence of it. But yeah, like, well, we haven't exactly seen it with the naked eye or what have you. Now, you mentioned, of course, Carl Sagan being a big inspiration. Does Arthur C. Clarke ever enter your mind when you're talking about missions to Europa?
Yeah, and I was pleased to see that Arthur C. Clarke's 2001 featured in your Zoom background when we met just a few minutes ago. Yeah, Clarke certainly figures into our imagination, and it's fun that both Jupiter and Europa featured in 2001 and 2010. In 2001, albeit it was Jupiter was the focus only in the movie and not in the book. I thought it was really fun to go back and read the book when I started at JPL and to realize that Iapetus was the target instead.
Yeah,
Um,
yeah, I remember that. Wasn't
yeah,
sure why.
yeah. So, but to your point about Arthur C. Clarke, um, uh, two fun points. We spent a lot of time thinking about landing on Europa, and it often came up during that study that in 2010 we were instructed to attempt no landings there. But Arthur C. Clarke had a habit of dialing into planetary science meetings in the 90s and the early 2000s, and we did get him on record saying that we had permission to land on Europa. So for what that's worth. Um, it was a fun thing to have and fun to have those interactions. I think science fiction feeds our imagination, has a really vital role in feeding our imagination and inspiring us to pursue these efforts. Um, and so much so that Arthur C. Clarke's 2001 is a motif for our science team. We have the monolith as the mascot basically for our science team, such that
Excellent.
we have a scaled model, a replica of a monolith at JPL that was the first one that was built for our science team for our first science team meeting in 2015. My wife actually had a role in orchestrating that construction, um, and she's someone in film here in LA. And then at our subsequent team meetings that we've had around the country, we've encouraged the organizers of those meetings to figure out ways to construct their own scale model monoliths. There are a number of those throughout the country now, which is really fun. So as our knowledge grows, the number of monoliths also grows.
Hmm. Yeah, and in fact, I wanted to mention something for our listeners. So, 2001, A Space Odyssey. In fact, I did a whole episode on that too. I mean, this is kind of my whole raison d'etre, you know.
Yeah.
Um, but yeah, 2001: A Space Odyssey. That was the film and book were released in 1968, and Jupiter features pretty prominently in 2001 because it's where. Oh, oh, hello.
Hello.
Oh, geez, sorry. Yeah, accidentally hit the power button there.
Aha.
Uh, did I cut out for a second?
No, you didn't. You were
Oh,
doing just fine. I did notice that there was a 5 minute warning almost 5 minutes ago.
oh yeah, don't worry about that.
Okay.
I extended it. Yeah.
Okay.
But yeah, we were running low on the 40-minute warning, so I just told it, well, give me more time.
Good, good.
Yeah. Anyway, because I mean, I'm just getting really into it here. The so yes, Jupiter is featured pretty prominently in the film version, but as you said, yeah, the book version it was around Saturn, around its moon Iapetus, where the main character at this point in the story finds the larger monolith, the one that right has been communicating with the one on the moon. And so this was all written before the Voyager missions had passed through the system, before there was any scientific speculation about a possible interior ocean, right? So it's interesting because 2010, the next installment, which was also made into a film. Have you seen it?
I have.
Oh yeah, good. Absolutely. I thought that film too was really, really great. Um, so in that film and the novelization of it, which yeah, the film was the adaptation of the Clark's second Space Odyssey novel. He made sure that the location was back to Jupiter and focused on Europa because, of course, at this point he worked that into the script, right? He worked it into the book. Speculation about an interior ocean and how if the surface ice were melted, Europa could become a habitable world. And yeah, that for me was really, really inspiring. But a question I have for you is, let's assume that that actually were the case, that terraforming efforts were put into place, the ice was melted to create an atmosphere. Could Europa actually would that be able to let the life loose, or would Europa simply fall to pieces because of its composition?
Oh, that's really an interesting question. Yeah, so the idea of oceanic moons, including around exoplanets, it's a possibility. The thing is, the lifetime I think would be short. You can imagine if Europa were a little bit hotter, it even might have been a little bit hotter in its earlier days, um, such that its ice were really, really thin. The ice could frequently break up, at least in places, and you could imagine generating enough outgassing or loss of water that you develop an atmosphere. The thing is, sustaining an atmosphere is difficult for a body the size of Europa, because as soon as the atmosphere is just a little bit warm, if you imagine an atmosphere like ours, the individual molecules of water would have enough kinetic energy that they would their average velocity would exceed the escape velocity, and so you would lose the atmosphere pretty quickly. So this is a problem of having small moons. Now, if Europa were the size of Ganymede, or even larger, that lifetime would be longer. I don't have the numbers off the top of my head. I would expect that you're talking about tens of thousands of years at a minimum, before you lose all the water, and it could be millions of years. And for larger objects, it could be even billions of years. And so, yeah, so Arthur C. Clarke's idea of having a habitable Europa that's, I don't want to give away the ending, but a Europa that's warmed by a hot Jupiter, let's say, that would be a shorter lived scenario, at least in the geological sense, it would be short lived. It's still of interest to think about.
Oh, absolutely. So, if we could just speculate here for a second, let's assume that the Europa Clipper it finds potential evidence of biosignatures. The lander is sent there as well. It's dispatched to the surface. It's finding biosignatures in the water. If in fact there is life within Europa, I can only assume you've had fevered thoughts about what it might look like or what it might constitute.
Sure, sure.
Yeah.
We often, and as astrobiologists, we often answer these questions with a kind of a conservative view of, well, we think the amount of energy available for life is going to be less on Earth, and so what we imagine is microbes. Really, my thinking about what life on Europa might be like, since I tend to cleave to that more conservative answer, at least for now, while I'm sticking to that answer, that line of thinking really keys into my wonder for thinking about, Earth as another planet. But basically, Earth existed for much of its history in an unrecognizable form from what we see it today, right? The main form of life on Earth was single cellular. And so, until 500 million years ago or so, looking for life on Earth would also entail looking for microbes. Now, that being said, Earth also had photosynthesis. It had a lot of energy coming from the sun, such that I expect that if you pulled up to Earth with a spacecraft, you'd see the signatures of life from orbit in terms of signs of photosynthesis, the green from the algae or from the cyanobacteria anyway. So yeah, I think it'd be really intriguing to find some kind of cyanobacteria or similar at Europa. And, that line of thinking makes me wonder, would it have DNA with the same base pairs, the ATGC, that DNA on Earth uses? Or was there an entirely different origin for life and on Earth and on Europa rather? And if so, might it have used different base pairs? Is there some physical reason why the base pairs that Earth life uses are preferred? So I think of this kind of thinking as really just fundamentals about how life forms, how common it is, and whether the rules for forming life are so strict or so I want to say simple, that putting together the ingredients for life is almost always going to give you similar life to what you find on Earth. These are the kind of things we can start to ask if and when we find life somewhere else. So in that sense, that's kind of what gets me most excited about looking for life on Europa. There's of course, I think what you're going for more the wild imaginings of what else could be there. If you go to the aquarium, there's a lot of weird stuff even on Earth. And in Earth's history, there were a lot of other weird body forms that were tried out that didn't last. Um, but just looking at the diversity of types of starfish, there are a lot of things out there um, that you could imagine existing on Europa, different types of jellyfish.
Mhm.
Um, People have imagined different types of octopi. In fact, the movie Europa Report has a really nicely imagined octopus. Um, I had the good fortune of advising on that movie, which is a whole other dimension to my science career. Um, yeah, so um, in my more optimistic moments, when I think about oxygen making its way into Europa's ocean, I imagine fish, I imagine an ecosystem with life clinging under the ice, scavenging the oxygen coming from through the ice. I sometimes even imagine, given that the ice is possibly tens of kilometers thick, I imagine vertical rivers of meltwater generated by tidal heating, and these channels of water flowing through the ice and microbes living in those channels, or even larger forms of life that are living off the oxygen. There's all kinds of things that might exist. It really depends on how much chemical energy is available. And so what I'm excited about with Europa Clipper is that we're going to get a sense of the distribution of chemical energy around Europa, the spatial distribution, both laterally around the surface, and then within the ice and within the ocean. That's just going to be even more food for the imagination, to think about what kind of ecosystems might exist, not just what kind of individual organisms might be there.
Yeah. And in fact, well, a couple points here, but I'll try to take them off one at a time. In fact, a lot of the current speculation and sort of theoretical predictions, right, is that there's likely hydrothermal vents around the core mantle boundary. That's part of yeah, that would be what allows for ocean worlds to maintain their liquid water oceans, and that these call to mind hydrothermal vents on Earth, which, as I understand it, modern evidence suggests that the earliest life on Earth may have actually started around these vents, like fossilized bacteria that's billions of years old.
So yeah, those are both some really, interesting, compelling points about Europa and ocean worlds in general. Europa in particular, because of the analogy to Io and the possibility of really intense tidal heating, has the best chance of having hydrothermal systems. That said, we don't understand where the exceptionally high heating in Enceladus is coming from, and it's possible that that heating also attributes to a significant amount of heat in the silicates in the rocky seafloor and below. And we're still trying to figure out how that might work. At the same time, it's important to keep in mind that the shallowest parts of Europa's seafloor are going to be under immense pressures, higher than on average at the base of Earth's ocean. And so how geology works under those conditions, whether you can get low enough pressures to break the rock, to get fractures and fissures, and whether you can mobilize lava rather than keeping the rock in a frozen, hot, kind of more runny form rather than forming volcanoes. Those are open questions, and some of that will remain to be seen. There's a lot of modeling work happening right now suggesting that the high pressures are really make it really difficult to develop hydrothermal systems. That said, yeah, so seamounts on Earth, mid-ocean ridge spreading centers in the middle of the Atlantic, these are places where you do have, volcanic activity, a couple of kinds of volcanic activity. You can have active volcanoes at the mid-ocean ridges where you have basically lava just below the surface or very hot rock just below the surface. And the gradients in temperature are so extreme, you end up dissolving iron and sulfur and things in a way that they're not chemically soluble at the lower temperatures in the ocean. So you have these plumes of black material spewing out of these systems, these chimneys, and rapidly precipitating out. So you can have these kind of clouds of material forming. Long story short, though, you have hydrogen sulfide and other basic molecules coming out of these systems, and there are whole communities of organisms that are scavenging materials out of these chimneys. A special kind of tube worm. It's basically an aggregate of microorganisms, single-celled organisms that live in these worms that scavenge hydrogen sulfide and other materials out of the stuff coming out of the vents. It's really amazing that you have these systems that, for the most part, thrive just from the chemical energy from these volcanoes, not on photosynthesis. Although there are also organisms at these systems that benefit from organic materials that are ultimately coming from the continents or from the ocean. So, they're scavenging materials that fall into the ocean. So there is some connection between the subsurface ecosystem on Earth and the surface ecosystem. Now, but getting down to those depths that are more comparable to what you have on Europa, where the pressures are up to 10,000 atmospheres, you do have organisms that survive, and those are different communities. And we still have a lot of exploration to do of our own seafloor, such that perhaps we will discover some kind of volcanic activity or at least hydrothermal activity at greater depths, more comparable to what we find on Europa.
And I'm glad you mentioned Enceladus too, because one thing that's happened with ever since the Voyager missions buzzed through the Jupiter system, we've gone on to find similar conditions, right, or similar lines of evidence for many, many other moons out there. Hence the term ocean worlds, right? It's plural, and so that includes Ganymede, possibly Callisto, Enceladus, Titan, and the list goes on. Who am I forgetting here?
Yeah, I think you've got the main ones where we have really compelling evidence. Pluto, there's been, there was a single flyby by the New Horizons mission. But the heart shape on Pluto is suggestive of a low density region that in some models is interpreted to be a subsurface ocean. And people have pointed out that the nitrogen on top of that layer, which if you look at it is really cool. It looks kind of like the convection currents if you put cream in your coffee, you can see stuff churning at the top of the coffee. There's something similar happening in the nitrogen, and it's a similar physics. It's basically it's actively churning around because the solid nitrogen has a pretty low viscosity. But back to my point, the solid nitrogen has a low thermal conductivity, much lower than ice, and so it basically works as a blanket. And so based on that, it's kind of reasonable to suppose that despite being such a cold and small world, Pluto might have retained enough energy to keep some liquid water underneath the surface. So yeah, the more we explore, the more weird stuff we find. And we're still thinking about. In fact, NASA has a priority to send a mission to Uranus, where Miranda and Ariel and Iapetus and Titania are moons that are similar in their orbital distance and that is their orbital configuration, and in their size to some of the moons around Saturn. So there's a lot more to find out. I can go on. There are others as well that are possible
Yeah.
candidates as ocean worlds. But you named the ones that are biggest and
Yeah.
for which we have the best evidence.
Yeah.
Yeah, Titan and Ganymede are just other kinds of worlds. They're more comparable to the size of Mercury, right? And we have good evidence for oceans there. And those oceans are probably hundreds of kilometers thick, hundreds of miles thick. Um, and so thick that at their base they probably have compact forms of ice that are dense and sink to the bottom of the ocean. So they're sandwiched. The oceans are sandwiched between different types of ice.
Yeah. Well, that too, that does make the possibility of life in hydrothermal vents and rather bleak, doesn't it?
I don't know. There's been some interesting progress in that realm in the last 10 years or so. The thing about the high pressure ice layers is that at the top of the ice, it's not like you shouldn't think of it like a rocky seafloor at the top of the high pressure ice, because what's different is that the high pressure ice at the top where you interface with the ocean is at its melting point. And so if you had a rocky seafloor like that, you would have lava interacting with rock. And you could imagine that that's not a very stable situation. And so what that means is that you probably have fluids percolating the upper part of the high pressure ice. And what that also means is that you probably have fluids throughout the high pressure ice because you basically have a hot thermal profile through the ice. And so it seems likely that any thermal anomalies you get underneath the ice would be adequate to mobilize fluids. And so in that sense, at least, you have possibly like kind of low temperature hydrothermal interaction. Um, the that said, there isn't a lot of tidal heating in Ganymede or Titan. Instead, they have oceans because they just formed with so much material that it was hard for them to get rid of all their heat.
Hmm. Okay. So in the coming years, the way I see it, Europa Clipper will be something of a trailblazer, a pathfinder, right? It's going to be conducting the science that scientists have been waiting decades to do. And it is currently there's only one other mission on as far as NASA is concerned to investigate an ocean world, and that's the Dragonfly. Is that correct?
That's right. Yeah. So NASA has on the books the Europa Clipper mission, which will complete our prime mission around 2035. And around that time, with any luck, the Dragonfly spacecraft will be exploring Titan. And so that'll be those will both be entirely different from missions from anything we've seen before. For Europa Clipper, in terms of the science organization of the mission, the kinds of things we'll be able to see with the really high fidelity instrumentation we have and the way we've designed the mission for all the measurements to overlap. And so we'll be able to compare and just get a whole lot of information out of all those measurements. So I just expect that my field, the study of ocean worlds, is going to be turned on its head by what we find from Europa Clipper. And yeah, Dragonfly, flying around the surface of Titan, is just going to tell us a whole lot about Titan and in the weird ways that its surface weather and geomorphology manifests. Titan is more like an Earth-like world in that sense. But I also hope that as part of that mission, we're going to learn a lot about how its ice shell works and how thick its ocean is. Some of the same stuff that I'm excited to learn with Europa. I hope to learn about Titan using Dragonfly.
Yes. Well, I hope to have you back on the show so we can discuss that because Titan itself is a very interesting and unique world within our solar system, as far as we know. And yeah, the implications of its existence here, right? We assume that there may be many more like it out there, and there's speculation that there could in fact be exotic life there.
Indeed. Yeah, I'd love to come back and talk about Titan. It's a weird spot and it's a paradise for organic chemists for
Mhm.
all of the weird stuff that's there.
Yeah.
Lots of long chain carbon molecules. and probably a lot of other stuff too that we haven't detected.
And of course, all this has implications for exoplanet research. And in fact, there's even a theory, a Fermi paradox resolution theory that says that maybe the best places to look for life, that we got it wrong looking for life on terrestrial planets. We should be looking for ocean worlds in other solar systems. So that too is something we could definitely discuss.
Yeah, well, in general, I mean, even just with Europa, but with ocean worlds in general, we're exposed to a great diversity of different types of planets, types of worlds. But Titan in particular, I think, really points the way to, maybe there are Earth-sized planets that are cold like Titan and similarly carbon-rich like Titan that have, similar stuff going on.
Yes. Exciting times.
Yeah.
I'm very, yeah, I can only imagine how excited you must be with the launch of Europa Clipper just a few months away. Now, one other thing I want to ask is the European Space Agency. They launched their Jupiter Icy Moons Explorer, or JUICE, back in April of 2023, I believe.
That's right. Yeah, yeah. Juice is on its way.
Yeah. Now it is scheduled to reach Jupiter by 2034, whereas, yeah, Europa Clipper is launching in about 6 months and is going to get there at 2030.
So Europa Clipper is launching on a Falcon Heavy vehicle, a pretty capable vehicle that's going to give us a lot of oomph and get there faster. It just happens that the I think it's the Ariane 5 rocket that's the most capable rocket that ESA has. It'll take a little bit longer for them to get there. They're taking a more scenic route, but they will get there. And in fact, they'll be getting into their main tour of the Jupiter system just a little bit after we start ours. And so it's exciting to be at a place where now that we're finishing Europa Clipper, we have the time to speak with the JUICE science team and get back to thinking about some collaborative science between the two missions, which it happens is something we were trying to do back when I started at JPL, when NASA and ESA were considering a joint set of flagship missions to orbit Europa and Ganymede, respectively. It happens that ESA continued on that path, and the mission that they were studying culminated in the JUICE mission, which at the latter part of its main mission phase will orbit Ganymede.
And so, yeah, in fact, Clipper and JUICE will be studying these two ocean worlds separately, but there will be overlap too, as well, yes?
That's correct. So JUICE will have a number of flybys of Europa, some of them very close on with Europa Clipper. So we can imagine having data sets that are very comparable in terms of being able to look with similar sets of eyes at exactly the same behavior of Europa. So I'll leave the discussion of those details for another time, since some of them are subject to, making sure that our trajectories are exactly the same. But suffice to say, we're really lucky to have two very capable flagship missions in the Jupiter neighborhood at the same time.
Absolutely. Well, I want to thank you for coming on, and also I look forward to hearing of any information that starts coming back from these venerable missions. Yeah, much like James Webb, it's like, oh my God, it's actually coming together. And when the scientific returns start coming in, holy.
Yeah, it's a really exciting time with James Webb. And yeah, Matt, thanks for having me on. Yeah, I can't overemphasize how excited I am that we're about to launch, and we're gonna. It's only 7 years until we'll be getting our first data from Europa Clipper.
Well, best of luck to you and your colleagues. And like I said, I hope to talk to you again there and discuss more on this really fascinating subject, because there really is so much. It disappear down a dozen different rabbit holes, and still each one dealing with a separate icy moon, and still barely just scratch the surface.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.